我帮你调那个位置。嗯？我记一下。不对，就是
敲不中。
敲不中。
我刚刚没有听到中声。
这样吧。
开始了。Okay. I want to finish steady state electric current by telling you there's a very unique relationship between the leakage resistance and capacitance. Right? So in another sense, knowing the current value could help you in deriving the resistance, right? So we take a look at two conductors. It's forming some kind of capacitor, right? We add a battery to support the potential difference. So therefore, the conductor connected to the positive end accumulates positive charges, and negative charges are accumulated on the other conductor. So we know the field lines, the E field lines are generated from the positive end to the negative end. And if you pay the attention to the details, all the lines are normal to the conductor surface, okay, locally. We understand the simple system as a battery or as a capacitor, and we know how to calculate the resulting capacitance. But now the question is, what if in between the two conductors we have some imperfect dielectrics? When the two conductors are separated by imperfect dielectrics, due to the field lines, you might have the potential to allow current, right? So in this case, ideally, if you have two conductors acting like the capacitor, you don't want to have current flowing across the two conductors. But in reality, dielectrics are not ideal, so they do conduct slightly, and thus giving rise to some leakage current, leakage current, which is not intentional, but it might be there. And therefore, when you have the leakage current, you have something called as the leakage resistance. This is not entirely new. If you refresh your memory, when we talked about the transmission line, we actually included the leakage resistance G prime, conductance per unit length, into consideration. Right? So today I want to talk about it, and just to let you know, you have improved a lot. All right, so the capacitance defined by this two conductor is the amount of charge divided by the potential difference. And now that we know Q, the total charge included on a single conductor, is D making a closed surface integration, right? Divergence of D equals rho free, and that gives you this relationship. And voltage, the potential difference, is nothing more than the negative line integration of your E field intensity. So that is purely from the definitions. But D equals epsilon E, because now we're considering in this part where we have leakage current, right? So another way to formulate it is D is associated to charge, but it's also associated to field only. So D equals epsilon E, so we're just replacing the definition of D and E. And the bottom remains unchanged. Okay. What about resistance? Resistance is defined as the potential difference divided by the current value. As I stated, ideally, if you have a perfect capacitor, ideally there will be no current flowing across the two conductors, right? Ideally, if you have vacuum or you have perfect insulators, you don't have current flowing. But in the reality, you might be using a material that is slightly conductive to serve as your filler or displacer, right? You have to fix the two conductors in space. And that filling material might be slightly conductive, although it is a dielectric, so you have a small amount of current flowing across the two conductors. Therefore, you have some kind of leakage current, right? So once you have the leakage current, you have leakage resistance, right? So the potential difference is still defined as the negative line integration of your E field intensity. But I, your leakage current in this case, is nothing more than the leakage current density making a closed surface integration. So again, this is purely from the definitions. I is current density making a closed surface integration. But we know J equals sigma E. Once you have a conductive material, you can just take the consideration by knowing its conductivity sigma. Okay. Now, as we compare the top and bottom, on the top, we're trying to evaluate capacitance. At the bottom, we're trying to evaluate the leakage resistance in this system. Somehow, we see there are common parts, right? We both have voltage, but one is in the denominator and one is on numerator. So is there any way we can eliminate the effect of V, the potential difference? Well, we can eliminate the presence of V by multiplying capacitance to resistance, right? If we multiply these two quantities, this one is canceled by this one, and then in the numerator, we have the closed surface integration of epsilon E, and in the denominator, we have the closed surface integration of sigma E. And this integration, they're both calculated over the same surface. So basically, point by point, you have an evaluation of the epsilon to sigma ratio. So this is telling you, if you have a capacitor, right, with a known capacitance, and you have some kind of leakage current, you know there will be, unfortunately, some leakage resistance. Do you need to do additional calculations? No. All you have to do is, well, you know the material parameters, right? You know the dielectric materials permittivity and conductivity. Therefore, this ratio is actually known. All you have to do is you find out the capacitance of the system, and then you have the leakage resistance. Okay? You take the ratio of epsilon to sigma and you divide by C, then you have the leakage resistance. A very simple and straightforward way to find out the leakage resistance. Why is this helpful? If you still remember this simple coaxial cable, which we derived for its capacitance value, right? If you still remember, the capacitance value is 2 pi epsilon. Epsilon means the permittivity of the material filling between two conductors. But if in the practical sense, that dielectric is slightly conductive, so it's also having, well, in addition to epsilon, it's also having a slight conductivity, sigma. Then you don't need to do additional calculation. By our previous finding, R times C equals the ratio of epsilon to sigma, you directly find the leakage resistance. Well, if you don't believe me, let's come back to this table again for the transmission line. In the past, well, I showed you this to convince you that you have made abundant progress. You are now able to find the capacitance per unit length from this given coaxial transmission line. And now you have the capability to find out the leakage resistance, which was labeled in transmission line as G prime, right? Exactly the same result, right? G prime is the inverse of R, right? So you take the inverse, you have this result. So after 8 weeks, right, I'm showing you you're understanding more and more. Initially, you were forced to believe the transmission line can be represented by 4 basic elements: resistance, inductance, conductance, and capacitance. But now it's corroborated, right? Turn by turn, you have the ability to derive its resulting values, right? And that's what I call progress. So do you have questions? If not, I'm going to close E fields, and we're moving on to magnetic fields, right? Okay. We're now officially launching into magnetic fields. Again, according to the structure of the textbook, we are going to discuss about static magnetic fields. First, in free space, there's nothing. Okay? And then for the next hard point set, we're going to talk about static magnetic fields, but having materials. And then in the third PowerPoint set, we're going to talk about the boundary conditions and the energies associated with magnetic fields, right? But before I start, I have to warn you, throughout experience, most students find this part difficult. And the reason is, to understand about magnetic field requires some imagination, but in a practical sense, you have to review and understand vector operations carefully. Okay. Whenever we talk about magnetic fields, there are a lot of mathematical procedures involved, and especially a lot of curl operations. So please do go back to the video or the lecture notes for vector operations, divergence and curl, especially curl. Okay? So in this PowerPoint set, again, this is a new field quantity. So we are going to talk about the fundamental postulates first. I will spend a considerable amount of time to talk about it. And then we are going to introduce something called the vector magnetic potential. This is something you're not accustomed with. In our daily lives, we are very familiar with electrical potential, voltage, right? We use batteries every day, but we don't really know, we don't have daily life experience with magnetic potential. So this purely, like imagination for most of the students. And I have to confess, vector magnetic potential is something really mathematical. So after today, over the weekend, please do review vector analysis, right? And then we're going to talk about Biot-Savart law. I don't really speak French, but I don't know why. Magnetic fields are associated with a lot of French scientists. So I do practice pronouncing the names of these French scientists. So last year, I was very fortunate. I had 2 or 3 French students on exchange. So hopefully I'm pronouncing the names correctly. Okay. And for the very last part of this PowerPoint set, we are going to talk about magnetic dipole. Now, in the past, I spent a lot of time teaching you electric dipoles. But now, when we move into magnetic fields, we also have a counterpart, something called magnetic dipole. So after the introduction and discussion of magnetic dipole, we are going to compare the 2 dipoles side by side. Right? Okay, fundamental postulates. Again, whenever we talk about the field postulates, we will talk about the postulates in 2 forms. One is in the differential form, having divergence or curl. Another one is integration form. You have closed surface integration or you have the value integration, right? Then we will talk about the application of the Ampere circuit law. In Chinese, we pronounce it Ampere, but to my best knowledge, in French, it's Ampere. Okay, this R is F. Okay. Okay, so before we really move on, I think in high school, especially in the very last year of the high school year, we were forced to believe if we have magnetic field present in space and we have a charged particle moving at certain velocity, that particle would undergo some circular motion, right? And that associated force is called the Lorentz force. So that is your first encounter with magnetic field, right? So Lorentz force, F M is the charge carried by the particle and then multiplied by the velocity, making a cross product with magnetic field. What does that mean? Now, if I have a charged particle, Q, moving at certain velocity, but in space, I have magnetic field, right? This particle will feel a force in the direction and quantity defined by U cross B. So this force is a vector, right? So basically this particle would change its trajectory and goes out towards your eyes, okay? And as it changes location, it will undergo a cyclotronic trajectory, right? But this is something known to you, and it's called Lorentz force. But the funny fact is, when your high school teachers taught you this and forced you to remember this, they didn't spend time to explain the basic properties of magnetic field. Or I can even cast a challenge. Does anyone here know the difference between magnetic flux density and magnetic field intensity? So in the past, we encountered magnetic field. We understood the vector field quantity B, but B is actually called the flux density of the magnetic field. So think hard. How did I introduce E field to you? Let's come back to the blackboard. When we talked about E fields, when discussing the two fundamental postulates, we introduced divergence of E is equal to rho. And this E is the E field intensity. And when we have materials, then we introduce D, right? Then we introduce D, which is the flux density. But up front, now moving into magnetic field, we are introducing up front B as the flux density. Okay, so that is one thing already different. It's already different. So after today, I hope I can convince you electric field and magnetic field, they are by default very different. Okay. Okay. Take a look. Right? B. This is flux density. Okay. As compared to E field, we introduce the E field intensity. Okay. Now, before I move to the PowerPoint again, let's review your examinations coming up anyhow. Let's do a quick review. Divergence of E is equal to rho. Rho is the charge density, right? This is fundamental postulate 1. And then the second postulate tells you curl of E is 0. So you should be asking yourselves, what are these two postulates telling you? What kind of message are they telling you? The first equation is called Gauss's law. It's actually telling you, well, if you want to have some E field in space, you have to have charge, right? You have to have charge to produce the E field patterns. That's a message of the first fundamental postulate is telling you. What about the second one? Curl of this given vector field is always 0. What does that tell you? This postulate is telling you if you have a curl-free vector field, then this field quantity is a conserved field, 保守场. And at the same time, it is telling you this field looks like a radiant field if you have only a single charge. So together, combining these two, I showed you repeatedly, if we have a single charged particle, then the field lines are radiant. Right? It's radiant everywhere in a three-dimensional way. So actually you have a three-dimensional sphere, like the sun. Right. So whenever we look, if we want to understand about the field quantity, we look at the fundamental postulate. Basically, the fundamental postulates are telling you basically everything. Okay? And that is why the fundamental postulates are so important. As a direct comparison, for magnetic fields, the flux density has a 0 divergence. Now you have to think very hard. What does that mean in a physical sense, in a way that you can understand? A vector field, the magnetic field is also a vector field, but its divergence is always 0. Let me just try to write it for you, right, side by side. Divergence of B is equal to 0. Let me erase this one, it's too annoying. You compare side by side. E field, you take this divergence, it's non-zero. But for B field, the magnetic field flux density, you take its divergence, it's always 0. So right at this moment, are you able to tell yourselves what type of field is B? You might not be able to tell, but let's follow the discussion, right? For E field, divergence is not equal to 0, which means if you have charge, single charge, multiple charges, doesn't matter, as long as you have charges or charge in space, you have E field. So another way to appreciate Gauss's law is the source to create E field is charge. Now what about this? This fundamental postulate is telling you divergence of B is equal to 0. What does it say? What's the physical meaning of that simple equation? It is effectively telling you, hey, in the real world, I mean, at least in the conventional world, we don't have a corresponding single element, basic element that can create magnetic field. Okay? Basically, there is no so-called magnetic source or a single particle that can give rise to magnetic field. So the difference between E field and M field is so dramatic. Electric field, you can easily isolate a single charge, so you know it produces E fields. But for magnetic field, you don't have a well-isolated source. You don't have a single particle which acts as a source to generate magnetic field, because divergence of B is equal to 0. Okay? So that's an underlying physics being taught by this simple postulate. Right? You don't have a simple isolated magnetic source. In differential form, you have divergence. Divergence is always associated with the value integration. But then once you have value integration, you can invoke divergence theorem to have a closed surface integration of that field. So the same postulate, but formulated in an integral form, is the B field. If you have B fields in space, and you use a closed surface, and you try to evaluate the resulting field quantity over the entire surface, it's always 0. Now, what does that tell you? The same postulate, but written in a differential form, tells you, well, there's no isolated source to create a magnetic field. But in the integration form, this is telling you another message. A quite shocking message. If you cannot come up with a right picture now, let's come back to the E field. In E field, right, divergence of E is equal to rho. So if you calculate over a closed surface, D dot ds is equal to the charge, right? So the simplest closed surface we like to form in three-dimensional space is a sphere. Right? So in this case, this is telling you, well, if I evaluate the closed surface integration of the E field over this sphere, I have the amount of charge enclosed in that sphere. And this is telling you each location on the surface, you have field line penetrating across the unit differential area. Right? So basically, divergence of E is not equal to 0 means you have field lines penetrating or crosses the differential surface. But now the fact that B making a closed surface integration is always 0, always 0. Are you able to come up with the distribution or the shape of some B field lines by looking at this or trying understanding this formula? Well, I can again form a three-dimensional surface. It's a sphere, right, with a radius of r. Spherical surface. I form any type of surface, but and I do have B fields. But the result is the surface integration is always 0. What does that mean? That means magnetic field lines, well, close upon themselves. Take a good look. E field lines starts on the positive charge and terminates on the negative charge. So it's radiant. It's unidirectional, right? Unidirectional. Therefore, if the surface contains or encompasses a charge, you will have non-zero fields flowing out across the surface. Magnetic field. The field lines closest upon itself, right? So this field line is completely encompassed within the sphere. So basically, there's no penetration across the surface, right? Therefore, the surface integration goes to 0 because that field line is contained within the sphere. But the second case is, well, if the field line of the magnetic field is a very big loop, it's a very big loop. This field loop is bigger than your surface, but you have one going up, one going down, one going down, one going up, right? So basically, the net flux of this big closed loop magnetic field line is still 0. Now, as a summarizing statement, closed surface integration of B is always equal to 0 actually tells you the magnetic flux lines, the flux lines form closed loops. Right? So this is something I really want to nurture you, looking at simple equations, but you should be able to come up with very practical and conceivable physical pictures. So you should be able to draw out the resulting field profiles. All right, so in that process, you learn, you understand, so you're not memorizing, right? Second postulate, curl of B is equal to the vacuum permeability. This is permeability, okay, as compared to epsilon 0, which is permittivity. In magnetism, we have some constant called permeability, and J is something we just learned, the current density. Okay, simple enough. Let's go back to the blackboard. I like to have side-by-side comparisons. For E field, curl of E is equal to 0, right? But now, curl of B is equal to non-zero quantity, mu 0 J. Side by side, once again, you can see the dramatic difference between the two field quantities. One field quantity, E field, is having a non-zero divergence, but a 0 curl. Magnetic field is having 0 divergence, but non-zero curl. So this is really, really different. Right? It's just like two twin brothers or sisters, but who have very dramatic personalities. All right, so let me ask you a simple question. From the E field postulates, we concluded the E fields for a single charge is radiant, and I also said, therefore, the E field, curl of E is equal to 0 means physically E fields are conserved fields. Now, such a nice teacher, I already gave you the answer, right? Now we move on to magnetic field. Curl of B is not equal to 0. What does it mean? The second postulate also contains a lot of information. By dramatic comparison, right? Direct comparison and dramatically different, you should be able to address me without any doubt. Well, since curl of a vector now is non-zero, this field must be non-conservative. And what do we call a non-conservative vector field? Go back and check. I actually covered this in vector analysis. If a given vector has a non-zero curl, then this field has closed loop forms and therefore represents a vortex field. 漩涡场. Go back and check. We actually went over this in the past. Okay? So the second postulate for magnetic flux density is telling you directly up front, hey, this field is a vortex field. It is non-conserved. That is message number one. There is another message. What is the second message? I invite you to come back to the blackboard. The filming crews are very overworked. For each field quantity, if we want to understand it, we want to understand its profile, its pattern, and how it is being generated. So for E field, the reason you can have E field is you have charge, right? If you have charge, you can create E field. But for the first fundamental postulate of magnetic field, up to now, we already concluded there is no isolated source to produce magnetic field. So even though this first fundamental postulate is telling you how the field lines look like, but it does not tell you how the field loops are generated. And that piece of missing information is covered here. So now, please tell me, how can you generate this non-conserved vortex magnetic field? If you have current density, or meaning current, then you have the ability, you have the chance to generate the vortex magnetic field, right? So this is telling you, well, as compared to E field, where you have stationary charge, if you want to create magnetic field, you must have moving charges, right? Moving charges give you current. So you must have current in order to have magnetic field. And that is the reason why we introduce magnetic field directly after discussing static electric current. You need to understand about current in order to understand about magnetic field. Okay? So current, so again, let's come back to the assumptions. For steady state electric current, we assumed we have constantly flowing charges to give you conduction current. But at the same time, do you still remember what is the assumption? We only have the current, but there's nothing else. In that space, we only have current and maybe we have E field, but we neglected magnetic field. But now you know it's impossible. Why? Once you have current, you have magnetic field. Okay? This might be shocking. As I said, long time ago, all the basic assumptions when we covered static E field, steady state current are probably not practical. Okay? You have two charges, they either repel or they attract each other. How can you keep the space, keep the distance, right? So reality are very complicated, but you have to understand them from the beginning in simple situations where you make huge assumptions. So now the real world is once you have current, you have magnetic field. And J equals sigma E. So basically in our world, we have E field, we have current, we have magnetic field all together at the same time. That's the truth. Okay? Okay. Curl of B is equal to the vacuum permeability times the current density. This is written in the differential form. Oh, whenever you see divergence and curl, it's differentiation. We can also use Stokes theorem to have a line integration over a closed loop is the amount of current encompassed by that loop. So look at it again, and at the same time, I'm going to reproduce that on the blackboard. Let me reproduce it on the blackboard. This equation is telling you, well, if I really form a closed loop, right? This is my C. If this closed loop is having some current being enclosed inside it, then at or on this closed loop, I must have some kind of magnetic field lines, right? So in this situation, I have to ask you to pay particular attention to the directions of the field and the current. So right now, I'm trying to express, I have current flowing out into your eyes, okay? So we have to follow the right-hand rule. So when we perform the curl, and thus, the curl direction conforms to the direction of the B field, right? So when your four fingers are moving along this closed loop, the thumb points into the direction of your current. And that is the correct direction of the B field, right? So in this case, the B field is counterclockwise, 逆时针. So again, I'm showing you the B field lines form closed loop upon itself, and then when you have B fields, you encompass some kind of current. So basic current is the fundamental element that can generate magnetic field lines. Okay? But to maintain a steady current itself is very deep, right? As we talked about, if we want to maintain a steady state electric current, we need to have a non-conserved source, a battery, current source, voltage source. They are itself non-conserved. And therefore, that non-conserved source could generate non-conserved field. All right? So this is known as the Ampere's circuital law. The circulation of magnetic flux density can be used to determine how much current is being encompassed in that closed loop. So that is called the Ampere's circuital law. Right? So let me stop here. Next Monday, we're going to continue to understand, and we are going to use this Ampere's circuital law extensively. All right, thank you.